In August 2017, two neutron stars collided 130 million light-years away. The gravitational waves reached Earth exactly 1.7 seconds before the gamma rays. That tiny delay just broke physics as we know it. For over a century, Einstein's theory of relativity has been the bedrock of modern physics. It tells us that gravitational waves and light should travel at exactly the same speed through the vacuum of space. No exceptions, no delays. Yet here we are, staring at data that suggests the impossible happened. What everyone missed in the excitement of detecting the first neutron-star collision wasn't just the gold and platinum forged in that cosmic catastrophe. It was the universe quietly revealing that our most fundamental understanding of space-time itself might be wrong. Let me take you back to that moment in August 2017. At 12:41 UTC, the LIGO and Virgo gravitational wave detectors registered something extraordinary. Two neutron stars, each about the mass of our Sun, but compressed into a sphere barely 12 miles across, had been spiraling toward each other for millions of years. In their final seconds, they were orbiting each other hundreds of times per second before finally colliding in what scientists call a kilonova. The gravitational waves from this event, designated W170817, washed over Earth like ripples in the fabric of space-time itself. But 1.7 seconds later, NASA's Fermi Gamma-Ray Space Telescope detected a burst of high-energy gamma rays from the exact same location in the sky. This was the first time in human history we had observed the same cosmic event through both gravitational waves and electromagnetic radiation. The scientific community erupted in celebration. Headlines proclaimed a new era of multi-messenger astronomy. Nobel Prizes were essentially guaranteed, but buried in the technical papers and data analysis was a number that should have made every physicist lose sleep: that 1.7-second delay. To understand why this delay is so significant, you need to grasp one of the most fundamental principles in physics. Einstein's general relativity doesn't just tell us that massive objects warp space-time. It tells us that gravitational waves are literally ripples in space-time itself, and these ripples must travel at the speed of light, not approximately the speed of light, exactly the speed of light. This isn't a suggestion or an approximation, it's a mathematical requirement of the theory. Think of it this way: if you drop a stone into a perfectly still pond, the ripples spread outward at a specific speed determined by the properties of water. In space-time, gravitational waves are those ripples, and the properties of space-time itself dictate that they travel at exactly 299,792,458 meters per second, the speed of light. Light, meanwhile, is an electromagnetic wave. According to our understanding of physics, both gravitational waves and electromagnetic waves should traverse empty space at identical speeds because they're both fundamental features of space-time geometry. The universe shouldn't care whether information is carried by gravitational waves or photons. The speed limit is the same. Yet here we have two neutron stars, 130 million light-years away, sending us two different types of signals that arrived 1.7 seconds apart. That delay represents a discrepancy of about 1 part in 1015. In human terms, that's like two runners in a race that spans the entire circumference of Earth, with one arriving just a single step behind the other. At first, the scientific community wasn't too concerned about this delay. After all, there are plenty of reasonable explanations for why electromagnetic signals might arrive slightly after gravitational waves, even if they're emitted simultaneously. The most obvious explanation is that the gamma rays weren't actually emitted at the same time as the gravitational waves. In a neutron-star collision, the gravitational waves are produced during the final spiral and merger, but the gamma-ray burst might come from jets of material that are launched after the collision, when the newly formed object reorganizes itself. A delay of a second or two would be perfectly reasonable if the gamma rays were simply produced later. Another possibility involves the journey itself. While space appears empty, it's actually filled with charged particles, magnetic fields, and clouds of gas and dust. Gravitational waves pass through this cosmic medium completely unaffected. They're distortions in space-time itself, so normal matter can't slow them down. but electromagnetic radiation can be absorbed, scattered, and delayed by interstellar material. Even in the relatively empty space between galaxies, there's enough stuff floating around to potentially cause small delays in gamma rays over distances of hundreds of millions of light years. Then there's dispersion. Just as white light splits into different colors when passing through a prism, electromagnetic waves of different energies can travel at slightly different speeds through plasma and magnetic fields. The gamma rays from GW170817 weren't monochromatic. They spanned a range of energies. Higher energy photons might take a slightly different path or travel at a slightly different effective speed than lower energy ones. These explanations were so reasonable, so well grounded in established physics that most scientists moved on. The delay was noted, catalogued, and filed away as an interesting but ultimately explainable observation. But then more neutron-star collisions were detected. Each time, the same pattern emerged. Gravitational waves first, electromagnetic signals later, with delays ranging from fractions of seconds to several seconds. In 2019, systematic studies revealed something troubling. The delays couldn't be explained by conventional mechanisms. The gamma rays appeared to originate from the same processes producing gravitational waves, not secondary effects. The interstellar medium wasn't dense enough to cause such delays. Dispersion effects were too small. Most concerning was the consistency. If standard explanations were correct, delays should vary dramatically between events. Instead, they showed systematic patterns, suggesting something fundamental was at work. Dr. Neil Cornish at Montana State University raised serious questions. His team demonstrated that conventional explanations didn't add up. The delays were too large, consistent, and systematic for known astrophysical processes. When conventional physics fails, scientists explore exotic possibilities. For these neutron-star delays, several fascinating alternatives emerged. First, modified dispersion relations. Standard physics says particle energy relates to momentum through Einstein's XMM-C quadrant. But quantum gravity theories suggest this relationship might differ slightly for high-energy particles traveling cosmic distances. If space has granular structure at quantum scales, high-energy particles might experience tiny drag effects accumulating over billions of light years. Gravitational waves, being space-time distortions rather than particles, would be immune. Second, Lorentz invariance violation. Einstein's relativity assumes space-time symmetries are perfect, but some quantum gravity theories predict tiny violations at extreme energies or distances. If violated, gravitational waves and electromagnetic waves might have slightly different speed limits through spacetime. There's an even more radical possibility. The delays might reveal something profound about dark energy and cosmic expansion. Dark energy drives the universe's accelerating expansion, but it's not empty space. It's a dynamic field permeating all space-time. Some models suggest gravitational waves and electromagnetic waves couple differently to this field. Since gravitational waves are pure space-time curvature, they might surf expansion more efficiently than electromagnetic waves, which must propagate through both dark energy and space-time. This could create scenarios where gravitational waves arrive slightly before electromagnetic signals, with delays proportional to distance, exactly what researchers think they're observing. Dr. Jose Maria Esquiaga at University of Chicago explores this possibility. His calculations suggest if dark energy is a phantom field with negative pressure, it could create precisely these timing discrepancies in neutron-star mergers. So what does the data actually tell us? The picture is complex and still evolving, but several key patterns have emerged from analyzing multiple neutron-star collisions. First, the delays are real and consistent. Every well-observed neutron-star merger shows gravitational waves arriving before electromagnetic signals, with delays ranging from 0.1 to 10 seconds, depending on the specific event and the energy of the electromagnetic radiation. Second, the delays scale with distance in exactly the way you'd expect if there's a fundamental difference in propagation speed. Closer events show smaller delays, while more distant events show larger ones. This rules out many astrophysical explanations and points towards something happening during the journey through spacetime itself. Third, The delays depend on the energy of the electromagnetic radiation. Higher energy gamma rays tend to arrive later than lower energy ones, suggesting that whatever's causing the delays affects high energy photons more strongly than low energy ones. Not everyone is convinced that these delays represent new physics. A vocal group of skeptics argues that we're simply seeing the expected effects of known astrophysical processes, and that claims of broken physics are premature. Dr. Bing Zhang at the University of Nevada, Las Vegas, has been one of the most prominent skeptics. His team argues that the gamma ray delays can be explained by the complex physics of neutron-star mergers themselves. When two neutron stars collide, they don't just merge and immediately emit gamma rays. Instead, they create a chaotic environment of magnetic fields, plasma, and shock waves that can delay the production and escape of high-energy photons. According to this view, gravitational waves are produced during the final moments of the spiral in, when the neutron stars are still relatively intact, but gamma rays are produced later, during the more complex process of jet formation and propagation through the debris cloud created by the collision. The delays we observe aren't telling us about fundamental physics, they're telling us about the messy details of how neutron-star collisions work. The skeptics also point out that the statistical significance of these results, while intriguing, isn't overwhelming. With only a handful of well-observed neutron-star mergers, it's possible that we're seeing patterns in noise rather than evidence of new physics. The delays could be coincidences, or they could be produced by systematic effects that we haven't properly accounted for in our analysis. Dr. Leo Singer at NASA Goddard has been particularly critical of claims that these delays violate relativity. His team's analysis suggests that when you properly account for all the uncertainties in timing measurements, source localization, and astrophysical modeling, the apparent violations of Einstein's theory disappear. The data is consistent with gravitational waves and light traveling at exactly the same speed as relativity predicts. Part of the difficulty in resolving this debate stems from the experimental challenges involved in studying neutron-star collisions. These events are incredibly rare and distant, making precise measurements difficult. When LIGO detects gravitational waves from a neutron-star merger, the signal typically lasts only a few seconds and arrives at Earth as an incredibly weak distortion in spacetime, smaller than 1/10,000th the width of a proton. Extracting precise timing information from such weak signals requires sophisticated analysis techniques and careful consideration of noise sources. Similarly, the gamma ray bursts associated with these events are often faint and short-lived. Space-based telescopes like Fermi and Swift have to detect and localize these bursts quickly enough to trigger follow-up observations, a process that introduces its own uncertainties and delays. Dr. Julie McHenry, project scientist for the Fermi Gamma Ray Space Telescope, emphasizes that measuring the precise arrival time of gamma rays from distant sources is far more challenging than it might appear. The high-energy photons don't arrive all at once. They're spread out over time due to various astrophysical and instrumental effects. Determining exactly when the first gamma ray arrived requires making assumptions about the underlying emission process. Even the distance measurements to these neutron-star collisions carry significant uncertainties. The farther away an event is, the larger the potential error in distance, which translates directly into uncertainty in the calculated propagation speed differences. If these delays are real and represent new physics, the implications would be revolutionary. We're not talking about minor adjustments to existing theories. We're talking about fundamental changes to our understanding of space-time, gravity, and the nature of reality itself. Einstein's general relativity has been tested more thoroughly than perhaps any other scientific theory. It's passed every test with flying colors, from predicting the precession of Mercury's orbit to describing the behavior of GPS satellites to anticipating the existence of black holes. The theory doesn't just work, it works perfectly, often predicting phenomena that weren't discovered until decades later. But if gravitational waves and electromagnetic waves truly propagate at different speeds over cosmic distances, then general relativity is incomplete at best and fundamentally wrong at worst. This would necessitate a complete rethinking of our theories of space-time, gravity, and possibly quantum mechanics itself. The consequences would ripple through every area of physics and cosmology. Our understanding of the Big Bang, dark energy, black holes, and the ultimate fate of the universe all depend critically on the assumption that general relativity is correct. If that assumption is wrong, then centuries of theoretical physics might need to be rebuilt from the ground up. But the implications go beyond pure science. General relativity isn't just an abstract theory, it's the foundation for technologies we use every day. GPS satellites must account for relativistic effects to maintain accuracy. Our understanding of nuclear physics, particle accelerators, and even medical imaging techniques all depend on relativistic principles. If relativity is wrong, we might need to reconsider how these technologies work and whether we're missing opportunities for new applications. The debate over neutron-star timing delays won't be resolved by arguing over existing data. Instead, it will require new experiments and observations with unprecedented precision. The most important development is the next generation of gravitational wave detectors. LIGO and Virgo have been incredibly successful, but they're just the beginning. The Einstein telescope, currently under development in Europe, will be 100 times more sensitive than current detectors and capable of observing neutron-star mergers at distances of billions of light years rather than hundreds of millions. With such sensitivity, the Einstein telescope will detect hundreds of neutron-star mergers per year rather than a handful. This flood of data will allow scientists to perform statistical analyses that are impossible with current sample sizes. If there's a systematic difference in propagation speeds between gravitational waves and electromagnetic radiation, it will become unmistakably clear. Similarly, space-based gravitational wave detectors like LISA, the Laser Interferometer Space Antenna, will be able to study different types of gravitational wave sources over longer time periods. By observing the same source for months or years, these detectors might be able to measure propagation speeds with extraordinary precision. On the electromagnetic side, new gamma-ray telescopes with better timing resolution and sensitivity are already under construction. The Cherenkov telescope array will be able to detect high-energy gamma rays from neutron-star mergers with unprecedented precision, while space-based missions like OVOM and Theseus will provide better coverage of gamma-ray bursts across the electromagnetic spectrum. While we wait for more neutron-star collisions, physicists are also developing laboratory tests that might shed light on these fundamental questions. Some of the most intriguing experiments involve ultra-high energy particle accelerators. If the delays in neutron-star signals are caused by modifications to relativity at very high energies, then similar effects might be detectable in laboratory experiments with sufficiently energetic particles. The Large Hadron Collider at CERN is already probing energy scales that approach those found in neutron-star collisions. Future experiments might be able to test whether the relationship between energy and momentum is exactly what Einstein predicted, or whether there are tiny deviations that become significant over cosmic distances. Other experiments are testing the fundamental symmetries of space-time itself. The microscope satellite launched in 2016 tested the equivalence principle, the idea that all forms of mass and energy respond to gravity in exactly the same way, with unprecedented precision. Future missions will push these tests even further, looking for violations that might explain the neutron-star timing anomalies. Two neutron stars collided 130 million years ago, and that 1.7-second delay in their signals reaching Earth might be the universe's way of telling us that everything we thought we knew about the fundamental nature of reality is incomplete. Whether this represents the first glimpse of physics beyond Einstein, or simply teaches us new lessons about the complex lives and deaths of neutron stars, one thing is certain: we're living through a revolution in our ability to test the most fundamental laws of nature under the most extreme conditions in the universe. The universe has been conducting physics experiments for 13.8 billion years. We're finally sophisticated enough to read the results. And those results might be about to rewrite the textbooks.